Hi, um, and welcome to this last talk for the Edge AI track. So today I will be presenting the object detection on mobile using YoloV5. So this is a small project that we have decided to develop at SBB, which we have called SBB ML, and you can see here a little demo of the final result. So we wanted to bring object detection directly on mobile, and the motivation for that is really standard. That is, we don't want to depend on internet. We want the data to stay on the mobile phones, that we don't have any privacy issues. And we also wanted to have a fast inference time, if possible, real-time inference. Concretely, the goals of this project was to facilitate the deployment of a machine learning model on a mobile device. And for that, we have two steps. The first one is we need to take a machine learning model and convert it into a suitable format for mobile. And then we also need to develop some libraries in order to have efficient inference on mobile. And finally, we share all this project on GitHub. It is all open source. So now let's take a look a bit of how we did it. So it is really standard. We decided to take the YoloV5 model because it is open source, it has a good performance and a great community. Now the model is written in PyTorch and so also trained in PyTorch, and we trained the model on NVIDIA so that it goes faster. We have a large amount of annotated data, which is really important. So we have a data set of around 100,000 images, and we consider 150 objects. The YoloV5 model comes in different sizes, which will be important later on when we choose which size would we actually use on which mobile. Then once we have a trained model, we need to convert it into a suitable format that we can be used on an Android or iOS phone. For iOS devices, we use CoreML, and for Android devices, we use TF-Lite. We also include the normalization and the post-processing inside the model. So as you may know, the YoloV5 model outputs many predictions, so for all the bounding boxes, and then we need to filter them, and we use the non-maximum suppression algorithm. And then only we get the relevant detection. So we wanted this part to be included in the model so that it could be easier to use. We also use quantization in order to reduce the model size, and for that we use either float 16 or integer 8 quantization. So now for the inference. So on Android, we have a TF-Lite model, so we obviously use the TF-Lite framework in order to integrate the model into the app. And here we have different sizes of model and input resolution. The reason for that is that Android devices, they are really different from each other, so there is a lot of variety. And so a medium-sized model might be able to run on a high-performing device, but it will not be supported by a low-performing device. And so we needed to have different sizes so that we could have reasonable inference time on all kinds of Android devices. And the model can run either on CPU, GPU, or using the NN API. For iOS, we use the Vision framework, and it allows directly the integration of the CoreML model. And what is really convenient for iOS is that the CoreML engine chooses which hardware to run each layer on, so you don't have to worry about anything. For the inference, all the optimization is done directly by this CoreML engine, and as an engineer, you just need to deploy the model, and then all the work is basically done for you. So the main challenges came for Android and trying to support all types of devices. And also another challenge that comes for the two types of devices is overheating. So once the model runs for a long time on the phone will overheat, and with that, the inference time will increase a lot. So for that, we do not have any out-of-the-box solution. So what we did is, for the use cases that we have, we mainly created use cases in which we would not have to run the model for a long time. So to tie it all up together for this framework, so we called it SBBML. and it is all open source. It has many libraries, so we have the libraries for Android and iOS in order to deploy and run Inference on mobile. And these libraries, they also include other features such as object tracking, and they obviously have the support for GPU and for the Apple Neural Engine. We also have a library which contains the converter, that is to go from PyTorch to CoreML or TF-Lite. And this repository also contains all some trained models that we have, as well as some converted models. So now, why did we actually develop this library? Here is a small use case that we have for it. So this is the application SBBML. This application is targeted at the moment at blind and visually impaired people, and it contains all the information that you would have when you go in a train station. And the challenge that they had is that if they are on a platform alone and there is nobody there and the train arrives, they do not know which direction to take in order to find the doors of the train. And this is why we added this feature to the application, in which they can simply point in the direction of the train, and once the door is detected, the mobile phone will vibrate, and when they get closer to it, the vibration will intensify, and then they know that they are close enough to reach out and open the doors. We also have some other use cases, this time for internal use. So these are maybe some old examples. So this is for the application Repair and Clean, and this is an application that is helping the reporting process. So if somebody were to report that an object is broken, an object is dirty. At the time, the employees had to fill out forms, and this form would take a few minutes. And the part that was the most time-consuming is choosing which objects they actually want to detect. Because we have many, many different SBB objects, some of them will have different names, such as all the kind of displays and so on, and it would take maybe some time for the employees to select the right one, or even they would make errors. And so we decided to implement machine learning into it, so the employee can just take a photo of the object that they want to report, and then the model will recognize the object for them. And this allows us to speed up reporting time. We have other use cases such as material number detection. That is that we also want to detect exactly what ID the object has, and then damage classification. So for now, all the use cases that we have, I believe, are all meant to speed up reporting time. And this is it for this presentation. Do you have any questions? You can install the app. The feature, as I have shown with the doors, will come in the next few weeks. And yeah.
Could you just briefly explain what's special about YOLO and what's new in version 5? Because I don't know this.
What is special about YOLO?
Yeah.
So YoloV5 is a model that is based on the original YOLO model, so you only look once. That is, it is a one-pass network. You put the image, and then you get all the detection at the end. Now, YoloV5, it has a bit of a controversy because it is called YoloV5, whereas it does not really come for the YOLO people, but it has a similar functioning, yeah. And what is special, why did we choose it actually, was because it is open source and it has a great support and community, so that it is easier than to share, and if you have some problem, then there's a great community to share with and get solution for it. Yeah?
Is it only optimized for like Swiss trains or Swiss train station context, or will it be like extended to easily to some other contexts?
At the moment, the models that we have, they are all trained on SBB objects, so an object from here. Now, if we talk about the doors specifically, they can recognize all the doors from the trains that we have in Switzerland. So not only the SBB ones, but the BLS ones and so on. I have no clue how it would perform on the foreign train. But yeah, at the moment it is only trained on SBB objects specifically, but it can easily just be retrained with other objects. Okay, I think this is it. So thank you very much for coming today.